Hello, AP Physics. So, we've now learned a little bit about the conservation of energy, and it's now time to start applying it. And the thing is, the conservation of energy as a concept is pretty simple, right? Energy is never going to be lost from our system. It's either going to be transferred or transformed. But its application can get quite complicated, and that's why Chapter 8 spends so much time in a bunch of different practice problems. Because the idea isn't all that hard, there's not much to talk about, but it's the fact that its application becomes complicated. So we are going to go through a couple of these. The first one we're going to do is on page 190. It's going to be that spring-loaded pop gun. So we have our spring, and it shoots a projectile from its initial launch position up to some maximum height. So this distance here is going to be from an initial position of negative 0.12 meters to a maximum height of 20 meters. Now, this is a negative zero point 0.2 because there is this equilibrium point at 0 meters for the popcorn. Okay. We also know that the mass of our projectile is 0.035 kilograms. I've converted it for you. And so now what we want to do is we want to figure out what the constant K of our spring is. Okay, so we started this. Let's move this over to the side. All right, so now we can start to write out our work. So we know that the total amount of energy isn't going to be changed. So we can write this out as the change in kinetic energy plus the change in potential energy of gravity plus the change in potential energy of the spring. All is going to equal 0. So we know the kinetic energy at the beginning and the end, right, is going to be 0. So that's 0 minus 0, right? The initial minus the final. Then we can add up the different potential energies. So we're going to have an mgh final. They call it C, it's at point C, minus the mgh initial. Then for the spring, we're going to go from there's no potential energy left, right? Uh, it's completely at the equilibrium point to the 1/2 k x squared is equal to 0. So we can simplify this out and we can solve. So I'm actually going to walk through that work. The book kind of skips it all. So we have mgh f minus mgh I. And actually, the x squared is that I, right? They're at the same position. So k hi squared. Cool. So if we want to find out what this k is going to be, we're going to have to solve for it. So we move these two guys over to the right. So it's going to be 1/2 k hi squared is equal to, um, and we leave that negative there, mgh minus mgh. Then we're going to have to solve for this k, get it all by itself. So k is equal to mgh minus mgh. We're going to multiply this by 2 and divide by hi squared. Plugging in all our numbers, we should find an answer of 958 Newton meters. So just want to point out that we start off with our change in energy. We fill those in with our initial and final pieces, and then we solve symbolically, and then we plug in our numbers and we get our answer. Now, I know that some of you like to plug in your numbers a little bit early. If that's the case, just be careful about rounding. The next thing that we are going to be considering is forces of kinetic friction. So the book defines it slightly differently. We have work is equal to the change in kinetic energy plus the change in the energy that is internal, right? The thermal energy. It also writes it out as work minus that force of kinetic friction multiplied by the displacement is equal to the change in kinetic energy. So one way to think about this is that there's work being done in the system, but if we take away the force of or the work done by friction, then we're going to be left with the kinetic energy of that system. So let's consider the example on page 194, example 8.5. So in this situation, we have a box and we are pulling it across the floor with some force. Or sorry, that shouldn't be okay. Some force capital F. And it is being slowed down by the force of kinetic friction. It also has a normal force, which we will do as a lowercase n, and a force of gravity. These two things are being equal. Force of gravity, mg. And it is going to be displaced across the floor, delta x, till it is right over here, with some final velocity. So the book wants to know what is going to be the final velocity of our box once it has been pulled across the floor, some delta x. So it also defines all these numbers. Delta x is going to be equal to 3 meters. We know that the mass of our box is equal to 6 kilograms. That coefficient of friction, mu, kinetic friction, is equal to 0.15. And finally, the force applied is going to be 12 newtons. So these are all the numbers we need. So we're first going to set up our problem using that first definition. So work is going to be equal to the change in kinetic energy plus the change in the energy internal, right? Those are the two things that are happening. Um, we're not changing our potential energy either with a spring or with gravity. We're just pulling this box across the floor. And then we can alter our situation because we know that work is also equal to the force times the displacement. So this is how we're going to set things up. We know that work is going to be equal to, right? If we're going to have a change in kinetic energy, it's going to be the final kinetic energy minus the initial, which is 0, right? It's not moving at the very beginning, plus that change in internal energy. And that is just going to be the mu mg, right? Multiplied by the displacement. And this is going to equal our force times displacement here. And so we are pretty much done. This problem moves very quickly, but we'll just take a moment to look over it. So we want to know the amount of work in the situation, which is equal to the addition of the changes in energy, both for kinetic and internal. So here's our change in kinetic energy, right? We start off with no kinetic energy, so that's why we have 0. And then the change in internal energy is going to be the force of friction, which is the mu multiplied by the force of gravity, since the force of gravity is the same as our normal force, and then the displacement. And then the addition of these numbers should then give us our final force multiplied by our displacement. So now we can solve. So it's going to be 1/2 mv final squared equals the force times the displacement minus the force of friction multiplied by its displacement. Notice that this is the exact same equation as up here, right? Right? This is going to be the change in kinetic energy. We're subtracting that. Here's the amount of work that was done. Right? Same thing. You could have set it up this way if you wanted to as well. And then the velocity final, once we solve, is going to be square root of 2d force over mass minus masses cancel out here, so we get mu k and g. When we plug in our numbers and we get everything, you should find you have an answer of 1.8 meters per second. So either way, using this equation here or this equation here will get you the final answer. It seems like this one, since we already had k all by itself, right, which is going to have your velocity, this might have been a better way to start off the problem. But using the other equation works as well. All right, let's do one more problem, and I will let you look at the first example in the next section, changes in mechanical energy. So if we're dealing with mechanical energy, then we're going to be looking at the change is zero. Oops, let's change that color back to black here. So the change in energy is zero, but we have a delta K, right? Because we have a change in kinetic energy plus a change in potential and a change in the energy internal, right? We still have some friction. So notice how the potential energy is not explicitly gravitational. It could be a spring potential. So we'll be looking at that one. So look with me on page 198 with example 8.8. So I've drawn all four positions of our block at different times. We have some initial velocity. That initial velocity, it tells us at A is equal to 1.2 meters per second. We also know the mass of our block to be 0.8 kilograms, and that the K constant is equal to 50 Newton meters. And then we're going to be answering part B. So we also need to know that the mu of kinetic friction is 0.5. So let's scooch this over just a little bit here so that we got a little bit more room. Okay. So let's draw the forces that are acting on our block. So, and let's look at it because what we want to do is we want to find the maximum compression of our spring. So let's draw all of those forces at that time. Here we got N, we have mg. These two things are equal. And then we are going to have a force of the spring back this way. And then if it was moving, right, we would also have a force of kinetic friction. So these are the different forces that act on our box, right? If our box was completely stationary, there would be no kinetic friction, but we'll have it here just for a moment. So we know coming into the spring, the velocity is 1.2. And so we don't have to consider any time before x equals 0. So that means that the total distance that the spring will be compressed is also the distance that the force of kinetic friction will act on our box. So we are going to write our conservation of energy equation. So that's going to be 0 is equal to the change in kinetic energy plus the change in potential energy plus the change in the energy internal. It's all going to, well, we already wrote it there, is equal to 0. So let's write this out. Let's fill it in. We know that our final kinetic energy is going to be 0 now, right? It's going to stop at the end. So it's going to be minus 1 half m, and we call it VA squared. Then we are going to add the change in potential energy. So we know in the end there's going to be potential energy, but at the beginning there was none. So it's 1 half k x squared minus 0. And then plus our force of kinetic friction, which we can look up here, right? The force of kinetic friction is equal to mu kn, which is equal to mu k mg. So mu k mg, and it's the x here. I'll clean that up in just a moment. You'll see it look much better. Okay, so we know this addition and subtractions all get us to 0, so we can put our things together. So we know that we have minus 1 half m v squared plus mu k mgx plus 1 half k x squared is equal to 0. Now, what they do is they multiply both sides by 2 over 2. So that means that this goes away, and this goes away. And then you put a 2 in front of here. And then they use the quadratic equation to solve for their x, right? We want to find out how much the spring has been compressed. So that's when it gets a little bit ugly, but you should get 2 answers, right? Just with anything. When you plug this into the quadratic formula, you'll get 0.092, and you'll get negative 0.25. Both are in meters. And since we are choosing this to be the positive direction, then we will be compressing it with 0.092. So just to point out, right, we start off with our conservation of energy equation. We plug things in, and then we isolate the variable that we want. In this case, we got to use quadratic equation. It gives us 2 answers. The book explains that our initial answer with the frictionless case gives us a change in position of 0.15. And since there's friction, that tells us that we're going to have less of a delta x. So only 0.092 applies. And we are compressing the spring, which we usually define as the positive direction. So that's why we choose the positive answer instead of the negative one.